Hello there, everybody. In this video, we're going to start Chapter 8. We only do a little bit of Chapter 8. And we're going to start with arc length. So let's get started. So the idea is that we want to find the length of a smooth curve. And if we know the length of the line segments of a polygon, the idea is that we can approximate a smooth curve with polygons, or pieces of polygons. And so the idea is that if we increase the number of polygonal segments here, or polygonal, however you want to say it, if we increase the number of segments, then the length of the polygon gets closer and closer to the length of the smooth curve. So here we have a square and a circle, then a hexagon, octagon, and so on. You can see that the line segments total length is getting closer and closer to the curve length. So the idea is we want to define how to make line segments, like what it looks like, how we do it, and then take the limit as n goes to infinity. All right, so we're going to do a full treatment of this topic. So make sure you go back over this so you understand why everything works the way it does. So the idea is we have some curve here. It's blue. Y equals f of x. It has to be continuous, and it has to be defined on a closed interval. So it's not allowed to have any vertical discontinuities, like no vertical asymptotes. So the idea is to get this polygonal approximation, you join line segments of subintervals. It's the same thing we've been doing in this class when we've defined integrals. It's just a new kind of integral. So the idea is that you have xi, xi is just any of the x coordinates. There's n of them total, and each one breaks up the breaks up the curve, and we draw individual line segments that are that width. Then you evaluate the y coordinate at each of these xi points, and that gives us a point on the curve, right? So for example, here's x1. P1 is just x1 is its x coordinate. Its y coordinate is f of x1, whatever it happens to be. So we're joining up points, and then we're going to talk about how to find the lengths of these line segments. And it turns out it works out really nice. So the length is L, that's the curve, so that's what we're trying to find. And it's approximately the length of the polygon path, and it gets better as n increases. So what we do is we just define the length of the curve as the limit as n goes to infinity of these polygonal paths. So how to read this notation? This is just the distance formula between pi minus 1 and pi. So if you remember the distance formula, right, it's just the square root of x minus x1 squared plus the square root of y minus y1 squared. So that stuff's all in the notes, but just if you forgot what the distance formula is, you might want to look it up real fast, just so when I show you the formula, it's not surprising. In order for us to use this distance formula, our original function has to have a continuous derivative. So when you take the derivative, it can't have any discontinuities. If that happens, the function is called smooth. So what we're going to do now is we're going to set up the change in yi. That's just the difference in the yi minus 1. So if you look back at the picture here, let's go back to the picture. Even though x is at regular intervals, so delta x is equal subintervals, delta y isn't, right? Because the function can do it at once. The difference in these y coordinates might be different than the difference in these y coordinates. Turns out that it doesn't matter, but I'm just pointing out from a notation standpoint why the notation is different for y than it is for x. All right, so let's go back here. So we already know what delta x is, right? We've done delta x computations a lot in calculus, but this is how we compute delta yi. So there's your distance formula. And this is just how you find the distance between any 2 points on a curve, right? You plug in both x coordinates, you plug in both y coordinates, and then you do the computation. It's the Pythagorean theorem, right? What we're going to do now, though, is we know that this distance is always delta x because it's constant. It's constant. Well, it's a function of n, but if n is fixed, then it's a constant. So this whole thing just becomes delta x. This thing, we just defined it as delta yi. And we're going to be able to do some stuff with this. So I know it looks like it's getting uglier and uglier. Turns out it works out pretty nice. So what we're going to do now is we're going to apply the mean value theorem to the function on these individual subintervals. And it turns out that that means there's some number in each subinterval such that the mean value theorem applies. If you forgot the mean value theorem, you can jump on my YouTube channel and go back and look back in chapter 3 at the mean value theorem. Because I have my Calc 1 videos up. You can just, there's a bunch of playlists you can get into and find them. But the mean value theorem basically says that between any 2 points, the slope of the secant line between those points is some number, and there's some point on the curve where the slope of the tangent line is the same as the slope of the secant line. And that's what this formula is saying, right? It's saying that if we take the difference in x coordinates, multiply them by the slope, right? So the derivative at this xi star, you get the difference in the y coordinates. That's all that's saying. It's just the mean value theorem with the new notation here from chapter 8. So it doesn't matter where xi star is. It just has to exist. And I'll show you why pretty soon. So if all this stuff's going really fast, pause the video, go back and reread everything, and just try to keep up with it. None of this stuff is super duper advanced, but there is a lot of it, and it's hard to keep it all in your head if you haven't seen it before. Okay, so we've just seen that f of xi minus f of xi minus 1 is that's just the difference in the y's, right? Right, that's just this, right? Yi is f of xi, they're the same thing. And then the difference in the x coordinates is delta x. So this thing reduces pretty nice to this. So what we do now, so this is the formula from the previous page. Now what we do is we replace delta yi with f prime of xi star, delta x. And the reason we're allowed to do that is the mean value theorem. What this is saying is that there's some point on each subinterval where the change in y is just the slope of the tangent line times the change in x. It has to be true. And what this does is it gives us delta x's under the radical, and we can factor those out. So you just factor out a delta x from both terms, simplify, and you get this. And it's pretty nice, right? So it's the derivative squared plus 1. It's the square root of that times delta x. So we started to simplify it. So that means that this whole expression here can be replaced with this, right? We just showed that this is the same as that, is the same as that, is the same as that. So replace this with that. And it turns out this is the formula we're going to use, right? This is just a Riemann sum, right? If you have a limit, a sum, and a delta x, whatever's in here is what your integral is going to be. So that's what we're going to integrate. And it turns out that's exactly the formula that we're going to use for arc length. So memorize this formula. You're going to use it a whole lot in chapter 8. So it turns out that there's several different ways to write these formulas. We can use the prime notation, or we can use the Leibniz notation. It doesn't matter. Sometimes this is better because both of these formulas are used when we have y equals f of x. But the way that arc length works is that it's anytime we're able to find the arc length of a function, it's going to be 1-to-1 locally. So if you take small intervals, it's 1-to-1. That means we could compute it delta x or delta y. And you'll see that here in a second. All right, so let's do the delta x or dx arc length formula. Let's find the length of this curve. And then we're going to check your answer by noting the curve as part of a circle. So we don't really know anything about this circle. You could graph it if you want. You'll see that it's just the top half of a circle, but that's okay. And we're going from 0 to 1. So looking at the formula, you can see that we need that derivative first. That's always the first thing you do, is take the derivative of whatever the function is. Then you plug it into the equation for the arc length. So this whole thing is going to be squared. So I took the derivative here. I didn't show the steps in the derivative. I'm assuming you guys can do derivatives. So plug this whole thing in there. And remember, we're going from 0 to 1 in the x direction. We're given that because we're given y as a function of x. And then what you do is you simplify as much as you can. So negative squared goes away. X squared, and then this thing squared goes to here. And what you have to do is keep simplifying on the inside of the radical. So we can't reduce this, so you need to get a common denominator. And now you see that we have the common denominator. We're going to have 2 minus x squared plus x squared. So the x squareds are going to go away. 2 is a constant, so we can pull this 2 out of the radical and bring it to the front. So it'll come out as radical 2. And then we note that in the denominator, we're going to end up with a radical, and we want to use a trig substitution here, or one of the formulas from your handy-dandy formula sheets. Either way, you have to recognize that it's a squared minus u squared, so you have to recognize this as something squared. Well, it's the square root of 2 squared. And there's a formula for it, or you can do the calculation longhand. It's just square root of 2 times arc sine of x over radical 2 from 1 to 0. So if you're not sure what just happened, pause the video and go back, or check out the PowerPoints and go back. Make sure you can get it up to here, because that's the new stuff. From here, it looks like problems you've seen in either chapter 6 or 7. Right, so this is just arc sine of 1 over radical 2 minus arc sine of 0. Arc sine of 0 is 0. Arc sine of 1 over radical 2 is 45 degrees, right? It's pi over 4. And you're done. So this is a really good problem. It's a really typical sort of problem for this section, so make sure you can do it. Now, the second part of the problem said to verify that this is correct by noting that this is part of a circle. Well, this curve is 1/8 of the way around a circle of radius radical 2. So 1/8 of the way around 2 pi, because the whole length is 2 pi, times the radius, right? This is just a circumference calculation, right? 2 pi r is circumference, and we're going 1/8 of the way around, and you get the same answer. So the geometry agrees with the calculus, which is what we want. Alrighty, let's keep going. So it turns out the arc length formula also works if we're given x as a function of y. And you're going to see this in the next section as well. So however the function is set up and given to you, that's whether you go dx or dy. And again, you can use prime notation, but you know, it might be easy to mess this up if you're not paying attention. Or you might want to write it using Leibniz notation. So in the next problem, let's do Leibniz, just so we remember that the dy is what we're taking the derivative with respect to. So here, we're just going to set it up and then do everything on the calculator, because this function gets pretty ugly. So we want to just use technology. Or maybe you can't do the integral at all, right? All right, so we have x is a function of y, so we're going to use the formulas on this previous slide. And we're going from 1 to 4. So the first thing you do is you take the derivative with respect to y. Rewrite radicals as powers. Then we're going to be doing some algebra, so you want to put those powers back as radicals again. So make sure you can get all the steps from in between here and here. All right, now we're going to just plug this into the arc length formula. So we just found g prime of y, so you plug it in. We're going from 1 to 4. And you don't even have to simplify it. Just do it on your calculator. So on homework or a test, some of it might say set up and simplify. It might say set up. It might say solve. It might say solve by hand. Lots of options what you're required to do in a class like this. For a problem like this, I'm really just more interested in whether you can set it up. And so I'll let you solve it on a calculator as you've seen on previous exams. And that's all you got to do. You can simplify it if you want, but there's no reason to. All right, so that's number 2. All right, next topic, arc length as a function. So what we just saw is if you're given a set of x coordinates or y coordinates, finding the length along the curve from A to B or C to D. Here, we're going to look at from some point to any other point as a function. So the arc length itself becomes a function of where we're finding the arc length to. So that's a little bit different. It's almost more like what we did with derivatives when we first learned them in Calc 1. All right, so there is some notational stuff you're going to have to keep track of. There are shortcuts around it, but I recommend that you don't use the shortcuts because these problems can get real tricky if you're not paying attention. All right, so again, we have a smooth curve. Smooth means the derivative exists everywhere, like no discontinuities anywhere in the derivative. So if it's written y equals f of x, we're going to define s of x as the distance along C from the initial point, a f of a. So that's a given point. You have to be given the starting point. To the point Q, x f of x. Then s becomes a function called the arc length function, and it looks like this. So if you don't recognize this pattern, all I did was I took the formula for arc length and I rewrote it with t as a dummy variable. Because remember, we're going along the x-axis, but x is a number that we're plugging in, right? So if you get something that's a function of x, that just means any x value you pick gives you an arc length. But we can't put x here because you're not allowed to integrate a function with respect to itself. Like along the path. You're not allowed to do it. So this t is called a dummy variable here. And then what we do is, let me back up and show you. What we're going to do then is take the derivative of both sides of this. And what happens is we get the fundamental theorem of calculus kicks in. And it tells us it's just this equation with x plugged in minus this equation with a plugged in. And then over here, we're going to get a derivative, right? So it's ds dx, right? All we're doing is just getting the derivative on the inside again, but with respect to x, right? So here's x. So this is just f prime of x, which is dy dx. Those are interchangeable. And the dt goes away and the integral goes away. So you just end up with this. So if you forgot how the fundamental theorem of calculus works, go back and check it out. That's what we're using here. That's in chapter 4. And sometimes we write it as a differential. You just multiply both sides by dx. So either one of these is fine, just depending on how you're trying to do it. And we can also go in the dy direction too, right? As we saw in previous problems. So let's do one of these. Find the arc length function for the curve y equals x to the 3/2, starting at the point P0, which is 4/16. So we have y written as a function of x. So we're going to do the dx integral. Again, first thing you do, take the derivative. It's always first. So power rule works real nicely here. Then we're going to plug this into the formula. So there's our formula. So this is dy dx. Just plug it in. Now here we need to get this thing as a function, so we have to simplify it. You can't just leave it. Right? So that is the derivative. That's ds dx simplified. Now we can integrate this right? So this tells us like the base form for our fundamental theorem of calculus. So here's the formula we're plugging in. We just make this, we make x the dummy variable t, take this whole thing and plug it into the integral and go from 4 to x. Now it's a definite integral. So we're going to do the integral. We already know what the integral is because we just took the derivative, right? So we're going to do the integral, but then we're going to plug in x and then subtract the integral with 4 plugged in, just like an ordinary integral. Right? So when you do the integral, this is what you get. Again, I skipped the steps, but it's just a u substitution, nothing fancy. Then you plug in the upper limit and the lower limit. Simplify as much as you can, and you're done. So this second to last step here. This is the integral has been evaluated, but it's not simplified. This is simplified. For problems like this, many times you'll get things cancel and drop out, so I recommend you simplify for everything in Chapter 8. So what this is telling us is that if you're on the curve x to the 3/2 power, and you start at 4 and go any direction, the length along the curve, the amount of displacement along the curve, you just plug in x into this formula, and it tells you how far you've gone along the curve. So it's pretty neat. Alrighty. So that's it for this section. Pretty short. As always, if you have any questions, feel free to reach out. And I'll see you next video where we cover more of Chapter 8, where we apply these concepts. So until next video, I'll see you later. Bye-bye now.